Namaskar, welcome to Prakash on Basics. I am Prakash Zog and we've been talking of colors. Enjoying the beauty of colors is fun, but understanding the science and the theory behind it, behind all those thousands and more than lakhs of colors, is quite confusing. Um, Actually, colors can be classified in a number of ways. Some words that you have already heard of: primary, secondary, tertiary, complementary colors, analogous colors, spectral colors, non-spectral colors, cool colors, warm colors, shades, tints. Some of the terms I have already explained. Um, it is all this that we will try and simplify and clarify when we look into the theory of what colors are. We will break down this information again as usual into smaller bits or smaller parts, so that you will have chance to digest a lot of material over a span of time. Uh, Most of the colors words that we have used are quite straightforward, but there is a lot of misconception about the word primary colors. It is on their basis that different color theories are actually put forward. Um, Primary colors and their mixing is what really matters, and there are 4 or 5 different theories related to this, and they seem to be self contradicting. I'll try and simplify things in that context from today. uh, the colors we see in the spectrum uh, are the ones that make up the white light that comes from the sun. These are all known as spectral colors. Those that don't exist in the spectrum itself are non-spectral colors. They can't be produced by one single wavelength. They are produced by the combination effect of different wavelengths on the retina, which is then passed on to the brain. Um, the wavelength combinations are interpreted by the brain as different colors, and this is something that I mentioned some time back. I am just trying to remind you of things. There is one more thing that I must point out: there is no magenta because there is no magenta wavelength. There is no pink because there is no pink wavelength. Our brain is the one that is interpreting a combination of red, green and blue combination on the retina because of the cones, as magenta and pink and brown and so many others. So, these are all non-spectral colors. Uh, some of the colors mix to produce other colors, and they further mix to produce other colors and so forth, and the percentage of red, blue and green keeps changing in all of them as far as the cones are concerned. Let me go back. When I was in school, I was told that there are some primary colors, and these were red, yellow and blue, and they could be mixed to produce secondary colors and tertiary colors. But the question is, how do we mix them, and how do we get the other colors that we talked of? Later on, when I moved into higher levels of physics, I was to study that it is the red, green and blue diodes that produce all the colors on the TVs or variety of screens and in projectors and so forth. And then by then I had already learned from biology that there are red, green and blue cones on our retina, which are obviously the long, medium and short cones representing those particular wavelengths. All this led to a lot of confusion. It was obvious because right from the school days there was a doubt. They started colors by in science with Newton's disc, with 7 colors, and you spin it and you see white color. And when you walked into your drawing classroom, you had red, yellow and blue, and when you mix them, what you got is darkish brown or black, and these were said to be primary colors which produced all possible other colors. And then when you looked at beams of light, and if you had the red, green and blue beams, they would mix and produce white light. So there seemed to be a lot of confusion. We need to understand this, and that's what I am going to do today. The formation of secondary, tertiary and other colors is interpreted by two different methods. One by the artists, and this is typically referred to as the subtractive method, and there is a second method by which scientists, or basically physicists who worked a lot in light, they interpret it on the basis of additive method. Light sources of different colors, beams, diodes, lasers, they all work on the principle of additive color combinations, whereas pigments and paints and colors and dyes, they and powders, colored powders and so forth, they all work on subtractive and selective reflective properties. So these are two different concepts. Naturally, their primary colors are also different, and how they produce a number of colors, that also is different. So naturally there are different theories for them. Let us try to understand the old and our school theory of RYB, which is red, yellow and blue theory today, and then later on move on into the others. There are a couple of other terms that are now very common and known to people. When primary colors are mixed, they produce what is known as a gamut of colors. Gamut is a mathematical graphical method representing different colors in terms of their percentages, in terms of their primary colors. Instead of the x, y and z coordinates, they tend to use the three primary colors and then get different coordinate points for each of the colors, and these are seen, and many of you all must have seen them in so many different pictures occasionally. This is also, since it is XYZ combination, it is also known as color space. So this then is what we are going to talk of, the RYB theory, red, yellow, blue primary colors theory. It was introduced long back, 1840, when one of the persons who worked in physics on light, known as Brewster, he is famous for his Brewster angle. We will talk of that sometime later. And this works on, as I mentioned previously, on the subtractive principles. It is among the oldest and still used model for color mixing by artists throughout the world. The basic logic of this RYB theory is absorption and selective transmission or reflection of light. Actually, this is what happens when artists mix paints and pigments while they paint pictures. So many great painters and their work that we appreciate and which is sold for millions of dollars, all those renowned artists, right from Picasso to Da Vinci and others, they have all used this RYB theory, and that is what we need to understand. The Actually, the subtractive color model, that is the one that we are talking of, combines the hues, different reflected wavelengths from colorants. Colorants are the ones that give color, and these are pigments or paints or inks or dyes or powders, as I mentioned. And you can add white and black and gray and get a number of other tints and shades, something that I had mentioned some time back. But for all of them, the background to get a perfect desired color is to be white. So it has to be either white paper or white canvas that was used. How do we mix them? To understand this, one of the most popular methods is to talk of what is known as the color wheel. And if you look up on the net, you will see hundreds of different color wheels. Showing one of them is a copyright issue, so I am not going to do that. As a teacher, it is better that I draw my own diagrams, and so I have drawn a color wheel for you people. I'll show it to you. I have tried to compile and give all the possible information related to this theory there, and I'll explain things as you see this diagram. You will have to stretch your imagination to understand what I have drawn. I would also suggest that later on you can pause the video at this particular point and look at this diagram once more to try and grasp many of the things that I have already talked of. Hopefully this should be clear enough for you to see. This is known as the RYB model. I am repeating a few things because that is what you are going to see. It is used by all artists, as I mentioned, and it uses the red, yellow and blue as the primary colors, and this is basically a subtractive type of combination that takes place. P here represents the primary colors P1, P2 and P3, which are red, yellow and blue, as you can see them. S1, 2 is a combination of 1 and 2 primaries. Then similarly you have S2, 3 and S3, 4, 3, 1, and so these are the secondary colors. Let me remind you again that when you add a primary to a primary, what you get is a secondary. When you add a primary to a secondary, what you get is a tertiary. And then it is possible that you can split the wheel further down and get so many more colors. Usually the colors that are specified are when you talk of equal percentages of the combination primaries and colors, and those are the names that are usually given. If the percentage is different, then there is a shift in the color that you see, and you can also add white and black to all this. So if you have yellow and red, as you can see there, you are going to get orange, which is a secondary color. And if you take yellow and orange and add them together, you will get a shade that is closer to yellow, because that is the closer primary, and you will get yellowish orange. But if you add red and orange, you will get a reddish orange type of a color. So depending upon and vermilion or amber, as you can see in these two cases, and similarly you can get the remaining colors also. If you for example add yellow and blue, you would get green, and these would be the two primary colors that would be added. And if you have yellow and green, you would get greenish yellow, and if you add blue and green, you will get bluish green, and these would be the tertiary colors. And you can go further down the line as much as is possible. So this is how this chart seems to give us information. As I said, you can possibly pause this and look it up once more. But if you mix all three of them together, it is obvious that we get something that is darkish brown and blackish, rather than the combination of all the wavelengths that we have been talking of. So how do these primary colors mix to give a different color by absorption? Let's understand that. So let's do an imaginative work. Let's say I have a white paper. I paint a blue patch on it. I paint a yellow patch on it next to it somewhere, and then I mix blue and yellow and make one more patch on the side, which obviously, as we all know, appears to be green, which is totally different from that blue and yellow that we've been talking of. The blue part is because of a particular wavelength, the yellow part is because of a particular wavelength, and the green we know is an effect that is somewhere in between. But let's try to interpret it as it works out here. So what really happens? Something like chlorophyll, for example. Chlorophyll is green. So what really happens is, when white sunlight falls on it, it absorbs all the colors, most of the colors, other than green, and the green is the one that gets reflected back. So that's also going to happen to the two patches that I talked of. When I talk of the blue patch, it absorbs the other two primary colors, that is yellow and red, but it does not absorb its own color, which is blue, and neither does it absorb green, because it is not really on the primary scale as far as blue is concerned. What happens in case of yellow? It absorbs the remaining two primary colors, that is blue and red, but it does not absorb its own self, which is yellow that you see, and it does not absorb green also. Naturally, when I mix the two of them, the blue absorbs the yellow absorbs the blue, and none of them absorb the green. So naturally, it is the green that is the color that you tend to see. It is also obvious that the intensity will be a little lower than the original one, but that is how the combination works out. And you can do it for any other colors also. You could do it for red and blue and get purple, and the same process will happen, and then this process will keep on repeating as you go to more and more complex forms. And this then is how the original pigment theory, which all the painters have been using all along. So when you have a white wall and you paint a particular color, that is why, to get the exact shade, the exact color, the exact tint, the wall is first whitewashed and then the other color is given. Otherwise, that background is also going to be one more factor that is going to absorb color, and so the reflected color may not be what you really expect. So that's how, and that's being done by not just the painters, but the fresco paintings that were made, and even the aborigines and the others also. So you have and in India you have they use rice paste to give a background and then paint on it. And so the idea is that if you have white as the base, then all the other color combinations on top are the ones that are going to work on the subtractive principles that I just told you and produce the colors that you want. All this worked fine till science moved much ahead, and more colors were tried out. And then people realized that this red, yellow and blue did not give all the possible colors that people can identify. And so another set of different primary colors and naturally its own theory came forward. And in addition, there was a completely different branch of getting color by additive method rather than the subtractive method that I have been talking all along. So that resulted into another couple of theories. We need to understand them also because they are equally interesting. But that is something for next time. If you have liked whatever I said, please look up the charts again and go to the net, see all those color wheels rather than understanding the diagram that I showed as a typical teacher. Like and subscribe to this channel. Understand the beauty of colors around us. Understand how the painters must have tried mixing colors and getting a definite particular shade to obtain the result. Till we talk of the theories again next time, the remaining ones, many of them, because they are equally interesting. Let's meet again after another 15 days. Till then, Namaskar.